All right, my friends, let's take a look. For part A, I was hoping that if nothing else, you could fall back on if in doubt, expand it out. So first of all, just by nature of the idea of an infinite sum, it can be hard to imagine that you could add up infinitely many numbers and that your answer would end up being finite. And so part A is dedicated to the idea of that being okay. So let's see, for part A, if n was 0, you would get just 8 for your first term. And then if n was 1, you'd have 8 times 1/10, which I think for a problem like this, probably decimals make a little more sense for expressing basically 8/10. If n was a 2, we'd end up with 8/100. If n was a 3, you'd get 8/1000, and so on forever. And so notice that we are adding up infinitely many terms, like we're supposed to keep going and going and going. But for this one, I hope it's not a far cry of the imagination to say that your answer would end up being 8.8 repeating, which is definitely a finite number. As a matter of fact, you could express it as 8 and 8/9. So not only is it a finite number, but it's even rational. Let's see, if we turn this into improper fraction form, just to be extra nerdy, what would that be, 80/9? Anyway, and if you don't believe me, then grab a calculator and do 80 divided by 9 or 8 plus 8 divided by 9, and you should see that you get that 8.8 repeating that we got here. So there you go. So that's kind of the first thing I wanted to get taken care of, is that it is possible in certain situations to have an infinite number of terms that you're adding together and to still get a finite answer. And for geometric series, that can happen pretty easily. And really with geometric series, it's just a matter of what is your common ratio as to whether that's possible or not. For part B, it would be harder to get the answer just by term expansion. But I'm going to go ahead and start with term by term anyway. So for part B, you'd start with n equaling 1. And so we'd have 16. And then we'd plug in 2 for n, and we'd get 8. Plug in 3 for n, we'd get 4, etc. So we still have infinitely many numbers being added together. Make sure you have that plus ... after whatever you put down for your last term. And so the question is this time, would this add up to something finite or not? And it is harder to tell by looking at the expanded terms here. Some people are super wicked good at these, and they have really good guessing abilities. It kind of depends. But for this one, instead of doing term by term expansion, I've had folks try to use the formula that we used last time, which, remember, last time it wasn't for an infinite sum. It was supposed to only be for like an nth partial sum of a geometric, but the formula was that the sum would be your first term times 1 minus r to the n, where r is your common ratio, n is your number of terms, over 1 minus r. And so what I've had people do with that is try to use it here, which you kind of shouldn't, but you actually can kind of get away with it. And so let's see what would happen if you tried. So you'd get your first term, which was 16, and then 1 minus your common ratio is 1/2, and then the number of terms is infinity, and then over 1 minus, and your common ratio again was 1/2. And so look what happens. This is kind of cute. So what's 1/2 to the infinite power? Well, that would be 1/2 being multiplied by itself infinitely many times. And so I hope it makes sense that this piece right here would approach 0 as you just keep multiplying a half by half by half by half by half by half. Anyway, so you'd basically end up with 16 times 1, or 16 over 1 minus 1/2, which if you simplify that, you'd get 16 divided by 1/2, which actually, let me write this a little better. You'd have 16 divided by 1/2, which would end up being 32. And congratulations if for part B, for whatever reason, you thought the answer would end up being 32, because you were right, it is. And so basically what we ended up doing there was using this formula and basically letting the n value approach infinity, since n meant the number of terms, and in this case, you're adding up infinitely many terms. So for part C, we could do the same thing. If in doubt, expand it out, and then converting to this formula over here. And we won't always use this formula for this situation because it's really not what it's for. But we'll use it kind of at a for now situation. So, okay, so let's start expanding the terms for part C. If n was 1, what would we get? So negative 16, I think. If n was 2, I think we'd get positive 8, and then negative 4, and then positive 2, and then negative 1, and then positive 1/2, and then etc. So I hope it makes sense that like this one, you had a negative common ratio, but this one's actually even more likely to add up to something finite than the one we had before, because the way the signs are alternating. So anyway, so let's abuse this formula over here, shall we? So let's just like let n, the number of terms, be infinity. So the first term was negative 16, and then times 1 minus your common ratio was negative 1/2, and then we have raised that to the infinite power, and then over 1 minus negative 1/2. Okay, well, notice that this little fraction here, negative 1/2 to the infinity, that's going to go to 0. That whole thing is going to become 0. And so you'd basically be left with negative 16 over 1 plus 1/2, which would be negative 16 divided by 3/2, which if you flip and multiply, you get like negative 48 over 3. Is that right? No, because 16 times 2 is 32. There we go. And then if, mixed fraction, or sorry, improper fractions don't do it for you, what would that be? Negative 10 and 2/3. That works too. Here we go. All right, my friends. So now, before we go on, let's talk about where we're going with this. There is a formula that we could use that is simpler than kind of what I've been doing, but it has some limitations on it. So I think what we'll do, we'll come back to D and E, and I hope that you, just for the record, I hope that for D you got that it adds up to infinity. We'll come back and talk about that in a second. And then for E, this one actually alternates. It doesn't settle and equal anything. So this one alternates between, actually, let me word this differently. This one has partial sums that, oops, that alternate between positive infinity and negative infinity. This last one was super weird. So, but let's come back to the warm up in just a bit, and let's talk about the simple formula that we could use when you have a geometric series. It's actually like, it's a lot like the nth partial sum one, but easier to remember. So, so let's talk about that. Let's see. Do we have an example one here? Okay. So basically, think about what is the formula for the nth partial sum of a geometric series or sequence, depending on how you want to word this one. You're going to add them up anyway, so I guess I'll just say series. Okay, so the nth partial sum formula is this. So S sub n is first term times 1 minus common ratio to the nth over 1 minus common ratio. Well, this is what you get if you are adding up the first n terms, right? So if you were to try to transition from there to a formula for an infinite sum, you would basically need to let the number of terms, which is n, approach infinity. And so if you did that, you'd get, here's notation that we use for that. LIM is short for limit. So we'd be taking the limit as n approaches infinity of the sum of the first n terms. Well, that would equal the limit as the n approaches infinity of the right side of the equation up there, which was a times 1 minus r to the n over 1 minus r. Now on the right side, on this side of the equation, there's really only one part in the whole thing that has n in it at all. And so what I'm going to do is move the limit expression to be right next to the expression that has n in it. So I'm going to write like this. So this would equal a times 1 minus the limit as n approaches infinity of r to the n over 1 minus r. So I just moved that little limit thought close to the part that has n in it, since we're talking about n going to infinity. Now the answer that you get here really depends on the value of r. So I want you to think about what values for r, what kind of numbers would you have to have for r to make this whole thing approach 0 if n goes to infinity. And I hope it makes sense that you would need to have, r would have to be something between -1 and 1, not including 1 or -1. So if that r value is between -1 and 1, then you would, this whole thing, as n goes to infinity, this whole thing would approach 0, and you'd be left with a times 1 minus 0, also known as just a, over 1 minus r. And notation that we use for an infinite sum, instead of saying limit as n goes to infinity of s of n, we just call that s. So the point is this, and I think a lot of you guys, when we did the first couple warm-ups, you may have been thinking this on your own anyway, is that you could just do your first term over 1 minus your common ratio for an infinite geometric, as long as your common ratio is between -1 and 1. So let's come back up here and kind of notice that that's what we ended up doing anyway. For part B, your first term was 16, and we ended up doing 1 minus your common ratio. For part C, your first term was -16, and we ended up doing 1 minus your common ratio. Common ratio is -1/2, which is why we ended up adding 1/2. So it's still 1 minus your common ratio. For part A, we never really thought of it this way because the numbers were so cute, but we could have, let me go back and kind of like use the formula here. For part A, your first term was 8, and then 1 minus your common ratio would have given you 8 divided by 9/10, and then flip and multiply, you'd get 80/9, which, boom, is what we had. So there you go. Let's make sure we make this official. So this is the formula for an infinite sum of a geometric. And it's just your first term over 1 minus your common ratio. Let's put a memorization cloud around that. Oh, but it only works if your common ratio is between -1 and 1. Now you might be asking, what if your common ratio isn't between -1 and 1? If it isn't, then you're way better off just expanding the terms. So like, for example, with part D here, if we were to start expanding the terms, we would have gotten 2 to the 1, which is 2, plus 2 to the second, plus 2 to the third, plus 2 to the fourth, etc. And I hope it makes sense that like your terms themselves are blowing up to infinity. So when you add up infinitely many of them together, you would definitely get infinity. Now, if you had used that formula that we talked about, then you would have thought that it would have equaled your first term over 1 minus your common ratio. And so you would have thought that it all added up to -2, which makes absolutely no sense at all when you look at the terms you would have been adding. So that's all the more reason for you to only use that formula if your common ratio is a number between -1 and 1. And then for part E, again, your common ratio here was -2. So you would not want to use that formula. Instead, you'd want to fall back on just if in doubt, expand it out. So the terms would have been -2 plus 4 minus 8 plus 16 minus 32 plus 64 minus 128 plus da-da-da, and keep going like that. And so for this one, depending on like if you kind of like do subtotals, you could see that your subtotal, as you keep adding in the next term and subtotaling it, your terms are getting larger and larger in magnitude, but they're flip-flopping in signs, as in positive or negative, positive, negative. So that's why with part E, I said it has partial sums that alternate between positive and negative infinity. Hopefully that makes sense. So, okay, the point is, don't use, first of all, only use this formula if you're adding up an infinite geometric, but don't use it unless your R values are between -1 and 1, or you will accidentally say something at least mildly crazy. All right, my friends. With that said, let's have you guys try to evaluate each of the following sums. Part A is the sum as n goes from 1 to infinity of 5 times 1/7 to the n, and then you have parts B and C to consider as well. All right, see how it goes. Check in with me in the next video.